Hello, today we're going to finish up chapter 2. We're going to talk about power supplies primarily and diodes, how they're used in power supplies for basically turning AC, alternating current, into DC, direct current. After that, we add some filtering and voltage regulator, and voila, you have a power supply. So that's where we'll end up here. This chapter is split into two parts. I should have mentioned that during the first one, but you'll see that that's how it was split up in the slides here anyway. So a half-wave rectifier is basically one diode that is inserted into a power supply circuit. We have AC current right here, and that it's passed through the diode and then through a load, this load resistor. Now, current only passes in one direction, as you know, in a diode. So V out across the load resistor has this hump. It only shows the positive part of the AC waveform. When the current goes the other way, okay, this way, it shuts off. Current is zero. So we don't get anything. So what you're going to get is a hump and then nothing, and then another hump and then nothing. So that's called a half-wave rectifier because it only rectifies half of the wave. The other half is not present. Now that's fairly inefficient. Obviously, you're throwing away half your current. Fortunately, the load doesn't. The power supply doesn't have to supply anything because there's no current. But nonetheless, you're using basically half the power of your power supply. Now, if the diode is reversed, you're going to get the bottom half. That's if the diode is flipped around like this. Now, there's an inverse voltage when the diode is reverse biased. Okay, and that's a specification. This PIV is a specification of diodes. There's a very common diode called a 1N4001. It's 1N4000X series, actually. And there's 1N4001, 1N4002, 4003, and so on, all the way up to, I think, 7 maybe. But each one of those has a different peak inverse voltage. I think the one is can be 50 volts, and then it goes up from there. I could be wrong about that, but we can look it up. The idea is that the higher the peak inverse voltage rating, the higher voltage it can handle in reverse. So if you have a 120 volt RMS signal here, right, well, 1.4 times that is 160 or something like that, or 180. That peak inverse voltage better be that, because that's what you're going to get. Now, to do a full wave rectifier, in other words, to get both humps, we want to get both sides, this and that, you can use a center tap transformer and two diodes. During the positive half of the current cycle, this side of the transformer is active because the diode is forward biased this way. During the negative half, this side of the transformer is active and this diode kicks in. So you're going to get both humps. See if they have a picture of that. Yeah, so you're going to get both humps. I keep calling them humps. Both cycles of the AC waveform is coming out, and this is much more efficient. You're using a lot more of your input power that way, right? And you can apply KVL to find the peak inverse voltage. Now, the peak inverse voltage on this is going to be the secondary voltage divided by 2, because you only have half of it, right? It's center tapped. So that's a good thing. And then there's another very common rectifier arrangement called the full wave rectifier, full wave bridge rectifier. And that uses 4 diodes. And you kind of have to visualize it here. The transformer, it's not a center tap transformer this time. So the current path goes through diode 2, D2, through the transformer, and then through diode 1, and then through the load. For the negative cycle, it uses the other two diodes. Comes through diode 3, through the transformer, and then through diode 4. Now, you know each diode has a what voltage drop across. If they're silicon diodes, it's 0.7 volts, right? So you're actually losing how much? 0.7 here and 0.7 there from your secondary of your transformer. So if your transformer is, say, 24 volts secondary, you're going to lose 24 volts minus 1.4 volts, or 22.6 volts is what you're going to end up with at V out. And that's important. You have to take that into account. And the peak inverse voltage is, again, half of the secondary because you have two diodes and you split it between both of those. And this is peak inverse VP out, but that's for both diodes. Determine the peak output voltage current in the 3.3K load resistor V secondary is 24 volts RMS. Used a practical diode model. Okay, so here's an example. V peak is 33.9 volts. 1.4 times V RMS. You remember the peak voltage is 1.4 times, or V RMS divided by 0.707 is another way to look at it. So VP out is V primary, V secondary here. V peak secondary minus 1.4 is 32.5 volts. So 33.9 minus 1.4 is 32.5 volts. And then the I peak is going to be, this is 3.3K, so Ohm's law gives you a 9.8 milliamps with 32.5 volts across it. Okay, we build up to the power supplies here. That's what these are used for. So here's our AC input, full wave rectifier, and there's a filter. Now, if we didn't have a filter on there, let me go back a couple of slides, okay? If we didn't have a filter on there, you'd have these humps, these big bumps on your DC voltage. Now, this is, it's hard to say. It can't be considered DC because it's only going, the current's only going in one direction, but it's real messy, right? It's very, very unfiltered. So what we do is we filter it, and you get these ripples. Now it's called ripple, all right? And the filter is simply a capacitor. There it is. Now this is half wave rectifier, okay? This is just one diode. But look at the ripple on that thing. That capacitor is trying to hold up that voltage in between the humps. So that's okay if you're not drawing a lot of current. If this load resistor is really low, in other words, a really high current situation, it's going to really drain that capacitor voltage off. This droop right here is going to be much more severe if this is a heavy load. If it's not a heavy load, in other words, real light load, really high resistance, then the capacitor is going to hang out there a little bit, all right? It's going to be less of a droop. So it all depends on your application. Obviously, two diodes are more expensive than one diode. And if you beef up the capacitor to get rid of your ripple, that's going to be more expensive too and take up more space. So there's all these trade-offs when you're designing a power supply. And obviously ripple is affected by the RC time constant. A longer time constant, meaning bigger capacitor or a lighter load, as I just said, will cause less ripple. And here's a full wave rectifier set up on a secondary of a transformer. So this is very typical power supply. This is standard, regular issue power supply. This is what you'll see. You have a fuse, there's your power switch, there's the AC line, transformer going directly into a full wave bridge rectifier, and here's a voltage regulator. Now a voltage regulator is a part, usually 3 terminals, although there's a lot of different kinds, that has an input, an output, and a ground. And the whole job of a voltage regulator is to isolate the load out here from fluctuations on the input voltage. The other job of the voltage regulator is to maintain a steady voltage on the output if the load changes. Okay, so there's 2 different things a voltage regulator does. One is maintain the output voltage when the input voltage changes, and also it maintains the output voltage when the load changes. So for example, if your voltage regulator is a 5-volt power supply, a 5-volt voltage regulator, right? You might be feeding it 24 volts on the input. And that's varying because your AC line from the power company is kind of fluctuating a little bit. And so this is maybe ranging from maybe 22 volts to 26 volts. Okay, even though 24 volts nominally, 22 volts to 26 volts is what it is. Well, the voltage regulator's job is to keep this at 5 volts if it's a 5-volt voltage regulator, and it'll do that within a certain range. Or if you're sitting here at 5 volts and somebody loads up your 5-volt line, turns on a motor or something onto that 5 volts, and it results in more current flow, the voltage regulator's job is to keep 5 volts there. Okay, now these are not limitless, obviously. Voltage regulators are rated both in voltage and current, basically power. So they'll only supply a certain amount of power. They're not limitless. But there's a lot of different kinds of voltage regulators, and we get into that in integrated circuits in the spring. These 3-terminal voltage regulators also have 2 capacitors. This is one of the filter capacitors that we were talking about before. It also has this capacitor on the output, and typically that's used to handle load transients. So capacitors are like little temporary batteries. So if somebody throws on that motor, all of a sudden, it'll pull some current out of the capacitor quickly, which it can do, and then the voltage regulator will kick in and compensate for it. 2 specifications, as I was saying, on voltage regulators. One is line regulation, specifies how much the DC output changes for a given change in a regulator's input voltage. Here's the formula for it. Line regulation is delta V out over delta V in. That's the amount of change the output changes versus the amount of change the input changes times 100%. And this says that it's based on a DC input voltage change to regulator due to a change in AC line voltage. Yeah, okay, that's for an AC to DC power supply, but there's a lot of applications where you're going DC to DC. In other words, you might want to drop 12 volts DC down to 5 volts DC, like in your automobile or something, your car. Take your car battery. That 12 volts can't be used everywhere. Your USB, for example, outlet in your car, if you have one, that's not 12 volts. That's 5 volts usually, sometimes 3 volts, but it's most time 5 volts, okay? So there's a voltage regulator in there, DC to DC, but this formula applies nonetheless, okay? So if a regulator changes by 1 volt due to a change in AC line voltage, that's the input, and the output changes by 1.5 millivolts. What's the line regulation? I'll go through a formula here, hopefully. 1.5 millivolts divided by a volt times 100 is, voila, 0.15%. Sounds about right for voltage regulators. Now the other parameter is load regulation, specifies how much change occurs in the output voltage for a given range of load current values. So no load to full load is usually. So power supply or a voltage regulator has a full load rating. In other words, how much current it can handle. So if you take a voltage regulator and leave it just the output not loaded at all, don't hook anything up to it, you measure that voltage, that's voltage no load, VNL. And then you hook up a load to it which draws the maximum current that it's specified to operate under, maybe an amp or whatever it is. Then you measure the voltage again and put that there, be full load. Run this equation and you'll get the load regulation. Now, usually if you load a voltage regulator up, the voltage output goes down just a little bit. Okay, and I think there's an example here. DC output of a regulator changes from 5 volts to 4.96 when output varies from no load to full load. What is the load regulation? Well, we've got 5 volts minus 4.96 divided by 4.96, and the answer is 0.8%. Okay, next we talk about limiting circuits, and diodes are often not only used in power supplies, but they're used for limiting voltages. Okay, basically clampers. They call them clamps. Okay, so diode limiter basically is used all the time. A lot of times used for protection. We use it to protect inputs from excessive voltages, and it'll clamp that voltage. Right at this one, in case it's 0.7 plus this V bias. So basically you take the 0.7 volts and add this V bias to it. So if the V bias, I think there's an example here. If V bias 2.3 volts and the diode is here, you're going to get 2.3 plus 0.7. So this point right here is going to be limited to 3 volts. I think there's an example here. Yeah. Output tries to go above 3 volts, it stops it. And with multisim, you can see that. I think there's maybe an experiment we do in the lab for that. There's a scope trace. And if you flip the diode around, it's the same thing, only it clamps it at the opposite way, all right? So the V bias is 2.3 volts. You're going to subtract 0.7 volts now, and you end up with 1.6 volts. At the very bottom. Okay, it allows everything to go up here, but then it clamps it at the bottom at 1.6 volts instead of at the top. Now this kind of clamper, this is a DC restore. These are used in old TV sets. I don't know if they're used now in TV sets, but they used to use them as a common circuit there. This capacitor here, series capacitor, charges up to the voltage. That's one diode drop less than the peak voltage of the input signal. So it basically lifts up the sine wave or lifts up the signal. You only have this 0.7 volts down here at the very bottom, which is the diode forward bias. So it lifts up the whole waveform. Basically makes an AC waveform into a, I don't know, I guess a positive biased, in this case, AC waveform. And if the capacitor and the diode are reversed, you get it below 0 volts, negative clamper. We can look at voltage multipliers. I don't see these very often, okay? So we're not going to spend a whole lot of time on these. But basically what happens is the diodes basically charge these capacitors up, all right? This forward bias diode charges C1 up, and then when the current goes the other way, D2 kicks in and charges up C2. So you basically have two capacitors that are being charged up, and they're in series. So when you look at both of them, you end up with twice the voltage. Now the problem with this is that where's ground? There's really no ground in this circuit, so it's minimally effective in a lot of situations. Usually we use a switching power supply, which we cover that in the spring, rather than this sort of an arrangement. I don't spend a whole lot of time on voltage multipliers. You probably won't, not likely, you will not see this on an exam. Diode data sheets. You should go on digikey.com and check out some diodes. Here's the maximum reverse voltage, peak reverse voltage. It's the PIV rating. Maximum reverse DC voltage. So, and And what happens is if you exceed this maximum reverse DC voltage, what happens? Remember last time we talked about the breakdown voltage? That's what happens. It does break down. And it can damage the diode. Non-repetitive reverse voltage that can be applied across the diode. These are all very related. Matter of fact, they may not be specified separately. They may just be lumped into PIV rating. And maximum value of a 60 hertz rectified current. I don't know about this. Actually, there's usually just a peak current value, all right? Because this implies an RMS current because it's AC. Usually diodes are just specified in maximum current, and whether it's DC or AC, it doesn't matter. It could be AC RMS, but it's a maximum current, 1 amp, 500 milliamps, 2 amps, 10 amps, whatever it is. And then forward surge current, again, that would be an absolute maximum rating of the diode. Okay, there's some troubleshooting stuff that's in here. You can look at that yourself. Usually, when troubleshooting a circuit that has diodes in it, if it's a circuit that has an AC waveform in it that's going across the diode, what is the forward voltage drop supposed to be across the diode? Always 0.7 volts, roughly. If you see it 0 or you see it the full range of the power supply output or the transformer secondary, you know that diode is gone. It's an open diode, right? Or if it's 0 volts, it's a shorted diode. Okay, so those diodes are pretty easy to troubleshoot. A lot of times I'll power down the circuit completely and just take an ohm meter. I'll measure the diode in one direction and then measure it in the other direction. I should get current flow in one direction and not in the other. And you can use a meter for that, just an ohm meter. A lot of ohm meters have diode settings on them. You just set it for the diode measurement, and you'll see 0.7 volts or 0.6 volts across the diode in one direction. Flip the leads around, and you'll see nothing. Pretty easy to troubleshoot diodes. Also, next time or in a couple weeks, we'll do transistors, similar kind of troubleshooting. Okay? All right, so that's it for this week. That's chapter 2, part 2. So there'll be this PowerPoint along with the video. Okay? Take care.